To sum up what we said in the last video, how enzymes make reactions go faster, the answer is that reactions go slow because they have a very unstable transition state that they must get through before they become product. This arrow here, the activation energy in the absence of enzyme, is what makes the reaction so slow. So we'll put a minus E there. And in the presence of enzyme, the enzyme speeds up the reaction by lowering that activation energy and making it easier to get over the hump. So let's move on to the next page and talk about how enzymes do this. We're going to say that there are really three modes of catalysis, and this is a gross oversimplification, but it gets to the heart of how enzymes work. The first one is basically a phrase that we use to describe what we just said. Enzymes carry out transition state stabilization. What does that mean? It means enzymes, the active site, complement the transition state even better than substrate. We said earlier that the substrate fits into the active site like a glove, and that's certainly true. But what's interesting is the transition state, it was negative and tetrahedral in the case of chymotrypsin's transition state. It actually fits even better in the active site. So it complements it and draws it up and stabilizes it in a way that makes it easier to get through. So that's the most important one. But there are two others that we sometimes and often see in enzymes. One of them is called acid-base catalysis. And what this means is that the active site residues pull protons off or donate protons to the substrate. So remember, maybe we'll just flash back there real quick. Remember we said that water is not going to be a very good nucleophile, and it would be great if we could deprotonate it and get rid of one of those protons, then it could attack as a much better nucleophile. Well, that's true, and what enzymes sometimes do is they have, for instance, a residue that's very basic. It's a proton acceptor, and it can strip that electron off and make a water, which normally doesn't give up a proton very easily, takes it off and makes it much more active. Lastly, we sometimes see covalent catalysis. And what that means is that the enzyme and substrate form a temporary covalent bond. This can be a very powerful thing because sometimes the enzyme interacts with the substrate, actually forms a bond between the enzyme and the substrate, and that kind of covalent bond can really destroy other bonds in the substrate or create new bonds. So that's a very powerful way for this to happen. So I can tell you, this is, like I say, a very simplified view of how enzymes work. We would take this more like 3 hours worth in our upper level class. I'd certainly be happy to talk to you about these things if you're interested, but we're going to leave it at that right now for this video. We're going to summarize up how active sites work in two different ways. What we can say is that active site amino acids, let's make that note, active site amino acid residues can have two different roles. They can be specificity residues, that is, they can complement the substrate in order to select a particular or specific substrate or reaction. It really doesn't have anything to do with the actual chemistry that occurs. This is all about binding. It's all about, does the key fit in the lock? Does the glove fit in the hand? If it doesn't, it won't bind and won't do any chemistry. If it does, it will bind and it will do chemistry. That's the first side. The second side is the active site has catalytic residues. These are residues. Typically, it's going to be the side chain of the residue, and they participate in the chemistry of the reaction. And I'll just make a note as a nod to above, as acids and bases, for instance, or as nucleophiles for covalent catalysis, things like that. Okay, so that gets to the heart of the dual nature of enzymes. We have to bind, and then we have to do chemistry. The first is specificity, does it fit? The second is catalysis, how do we break that bond?